The code we've constructed up till now in previous chapters all uses what's known as the imperative style of programming. Now, imperative statements, these are like commands. So imperative programming is a focus on doing one command after another. Do this, then do this, then do this. And computation then arises from the changing values of variables across all of these commands in our code. Now that we understand functions, however, we'll begin coding using what's known as procedural programming style. This is a form of imperative programming where everything is organized as functions or procedures. We're still saying do this, then do this, but now we're focusing on describing units of behavior. This function accomplishes this. This function does that. And when we run them one after another, that's when we'll get our result. The motivation for using procedural programming is that it makes our code more modular and easier to understand. We can define all of the small subtasks of our solution as independent functions. Then we can test each individual function to make sure they're doing the tasks that they're intended. We can then change one of those functions without breaking everything else. And then once they're all set up the way we need, we can define a program at a high level in terms of calls to those smaller functions. And here's the general pattern for defining a program in terms of procedural design. Typically, at the start of the code, we define or specify all of the solutions to the subproblems that we'll need. So we'll create all of those helper functions. Then we define a function called main, which is a conventional name, not a required one, to describe the high-level solution in terms of calls to all of those functions that we've created. Then, as the last line of our code, the only thing that's not put into its own function, we make a call to that main function to start the process. By following the standard pattern, your code will be more maintainable, and others will have less difficulty understanding what you've written. As an example of programming in the procedural style, let's return to our rock, paper, scissors game. Now this is currently written in the generic imperative style, that is, say, without procedures. I've added a few optional features since we last saw this code. So we have the game loop, which we saw before, which continues up until the user says stop. I've also added some scorekeeping, so we have a score that starts at 0, and every time the user wins it goes up by 1, and every time they lose it goes down by 1. I've also added some input validation, so if the user doesn't say any of the allowed values, rock, paper, scissors, or stop, then this loop will continue. Note this condition says if the user is equal to rock, or if it's equal to paper, or if it's equal to scissors. These are all the allowed values. So if it is one of these, then this whole statement will be true. The not will make it false, and while false means exit the loop. Now if it's not one of those, so this whole statement is false, we say not false, which is true, and then the loop continues. Another way we could have said this is while user does not equal rock, and user does not equal paper, and user does not equal scissors, and user does not equal stop. These two forms for this condition are equivalent by a rule known as De Morgan's law, but I'll leave your Comp 1805 prof to explain that in more detail. So now what we're going to do is refactor all of this code to use a procedural style. This means we'll take each of the component pieces of our solution and put them into separate functions. As an example, we might factor out the part that generates CPU throws, put that in its own function, or the part that gets the user throw, or the part that judges the outcome of any given round. And once we have those all in their separate functions, we'll have one main function, which just coordinates how these parts interact with each other. So step one is to define our main function. Now, since we're starting with existing code rather than a blank page, we're just going to take all of the code that's here and shove it into a main function. Then we can refactor our solution into the parts to see the difference in styles. So here we'll call the main function RPS, since it plays a game of rock, paper, scissors. So I'll say def RPS with no parameters, remember the colon, and then we'll take all of our code and then just hit tab to indent it. So now this is all inside the function RPS. Next, we should be sure to include a docstring so as to describe the intent for this function. So I'll say this is the main function which coordinates the game loop and tracks the user score. So we have one main function, and we'll make sure down at the bottom of our code to call that function so that we can actually run this code. So we'll say RPS. Next, we'll start factoring out the subtasks into their own functions, starting with the CPU throw. So we'll make a new function, put it up at the top here. We'll call it def get CPU throw. Okay. And this will generates a CPU throw. So it will return one of rock, paper, scissors randomly. There we go. So there's our doc string for this new function. Then we'll just take the existing code and put it here. So the part of our code that manages the CPU throw is all of this, generates a random number and determines a throw based on that number. So we'll just say cut and paste. Fix our indentation, so all of this is inside the function. But we'll need to make some changes to this code just a bit. So instead of assigning values to a variable CPU here, we'll just say this function returns those values. So instead of CPU equals, we'll say return rock, or return paper, or return scissors. Now we have a function that generates a random number, and based on that number, we'll return one of either rock, paper, or scissors. Then in our main function, we will call our new function and store its result. So I'll say CPU equals get CPU throw. So that says get CPU throw, it jumps up here, generates a random number. It's either rock, paper, or scissors. Whatever that string is will get stored in the variable CPU. So when we're on this next line here, it's as though nothing has changed, right? It's still doing the exact same work, just in a different way. Next, we'll do the same for user input. So we'll create another function. Call this one def get user throw, which will say asks the user for their RPS throw and returns rock, paper, scissors, or stop. According to the user in this case. And again, we'll take the code from our main function. So that's all this stuff that manages the user throw. Cut and paste it into this new function. Fix our indentation. Again, we need to make sure that value exits our function. So we'll say return the value that they get. So assuming we got past this user validation loop, we'll say return whatever's in this user. So that should be one of these four, rock, paper, scissors, or stop. And then in main, back where we had all this code before, we'll just make sure to call this function. So we'll say user equals get user throw. And lastly, we can do this same treatment to the game results section of our code. So we'll say def game results. Now if we look at the text of this code, the output of this function is going to be dependent on its inputs, in this case the CPU and user throws and their relation between them. So we can move this code into our function, but in order for it to work correctly, these variables CPU and user need to have values. So we'll put those as parameters. We'll say CPU and user get passed into this function, fix our indentation again. Then if we have the values for CPU and user, so assuming those are two different throws, let's say rock and rock, then we'll do the comparison. So do these things equal the same? If so, we're going to print out a result for the user watching this game, but we also want to modify the score. Now score is housed in our main function, so we want to return that value back out to our main function. So we'll say, in any case, return 0 if it's a tie, return 1 if it's a win, and return -1 if it's a loss. Note in all three cases we were previously adding that result to our score variable. So now back in our main function where we call this code, we'll say score plus equals game result. And now we have to pass in values for the CPU and user throws, which are called CPU and user. Game results, plural. Actually, it is, I think, a singular result, so let's just put a singular result up here as well. Game result, singular. And that's it. Now all of our code, which is operationally unchanged, is written in a procedural style. So this should not change the behavior of how the game works, but just how the game is written. Notice how all of the instructions, if I scroll top to bottom, all of the instructions are now indented off the margin. They're all tucked into one of the many functions, with the singular exception right down here at the bottom of our call to main. So when Python sees this code, it sees def, okay, so that's a function, that's a function, that's a function, that's a function, and so far nothing's happened. It's read through 62 lines and done nothing. It gets to line 63 and that says, okay, start the code. So that'll jump into RPS, which will eventually call all of these other functions, and all the bodies of these functions will execute in turn. Notice also how much more condensed or clean the code for our main function is. This is approaching to be parallel to plain English. in terms of the descriptions of the actions that are taken. So we get the CPU throw, that almost matches our comment now. Get the user throw, that just matches a comment as well. So we have all of this, which is described by ending the game, display the throws, which just displays one thing, evaluate the results and update the score. That's, again, a single line statement. So our main function is a lot cleaner and easier to read, and the complex values of how do we get a CPU throw and what validation goes into a user throw, those are all tucked into the individual functions that manage those parts. So now let's test our game to make sure it still works. Again, it shouldn't be any different than before. So we'll say Python rps.py. Asks us for rock, paper, scissors. I could say yes, and it asks me again. I will say trusty old rock. CPU also throws a rock, and it's a tie. I can try again. This time it threw paper, and I lose. Tie, tie, and I won one. So you can see your scores going up and down with each win, loss, and tie, and the game seems to continue working until I hit stop. And it says, thanks for playing, here's your final score at the end. So that's great. The code works as it worked before. We didn't introduce any new errors. That's great. So this shows that we can express the same code in two different ways, but there are advantages to using the procedural style. For example, we can test the individual parts of our solution. So instead of just running the whole code, I can say python-i rps.py. So I'll open the code in interactive mode. Now it's going to start the main game, so I'm just going to say stop. But now I have the Python prompt available here with all of the code in front of me, so I can say something like get CPU throw. And that returns a CPU throw. And I can keep doing that to get different CPU throws, since it's a random number, and either do this programmatically or manually determine whether or not the results are coming up in a sort of uniform distribution, roughly 1/3 rock, 1/3 paper, 1/3 scissors, if that were a thing we were looking to test. We'd also test our other functions like game results. If we give it rock and rock, that's a tie. If I said rock and paper, then I win. So having our code put into these individual functions means we can test those individual parts of our code independent of the rest of the code base. Another advantage of procedural programming is that since our solution is so modular, we can very easily replace parts of it without affecting the rest of our code. For example, if we didn't want a CPU that's throwing uniform distribution of rock, paper, and scissors, we could create another CPU here. Call this def get CPU throw 2, just to avoid conflicts. And then we can say R is a random integer in the range from 1 to 100. And we're going to have a 50% chance of rock. So if R is less than or equal to 50, then we will return rock. And we can have a 25% chance for paper. So we'll say if R is, so it's not less than 50, then the next 25% brings us to 75. In that case, we'll return paper. And the remaining 25% of the numbers put into the else and return scissors. I can very easily in our main function just change this to get CPU throw number 2, save and run our code. And now the CPU should be throwing rock half of the time, paper 25, and scissors the other 25. Certainly seems to be using more rocks than normal. So that's the basic idea behind procedural programming. And again, that idea is that we take all of the code that we would normally write just in the margin in imperative programming, but we organize it as a hierarchy of functions calling other functions. That way those individual parts are contained into individual functions, which can be easily replaced or edited as needed.